Hello everyone, welcome to this channel, and in this video we'll do article 12.6 specific heat capacity, and we'll also see specific capacity for monoatomic gas, then for diatomic gas, then triatomic gas, and also the ratio will derive the ratio gamma that is important for your examination. Okay, so we'll see it through the topic we discussed in the previous chapter, previous video. That was the equipartition of energy. Each degree of freedom will contribute half kT. Through that we will about to bring find the expression, the value of the specific capacity. So let's begin this topic. Okay, and first of all, I'll just recall you what is specific heat capacity. So specific capacity is the amount of the heat required to raise, if I say specific capacity for 1 mole, molar specific capacity for 1 mole of a gas. If I have 1 mole of a gas, okay, 1 mole of a gas is there, and I have to raise the temperature of this 1 mole of a gas by 1 degree Celsius. What I have to do? I have to just give it supplied heat. Okay, how much heat will be supplied to raise the temperature of 1 mole of a gas by 1 degree Celsius? That is its molar specific heat capacity. Okay, if in case of mole, instead of mole 1 kg was there, then it will be simply specific heat capacity. Okay, so for 1 mole, molar specific capacity, for 1 kg it will specific heat capacity. Okay, also there are two more terms that you have seen in thermodynamics. Okay, that is for constant volume and constant pressure. Okay, suppose gas is filled in a container, and obviously the volume of this container cannot be changed, so the volume is fixed. So how much heat will be required to raise the temperature of this gas, that is at constant volume, by 1 degree Celsius? That will be its CV, that is specific capacity at constant volume. Okay, and if it is there is no such restriction, that the pressure is constant, it is open. Okay, in that case, the amount of heat required to raise the temperature by 1 degree Celsius, that will be CP, specific capacity at constant pressure. And question is there, very uh, general question: which is greater, CV or CP? Which is greater? And you can clearly see, if you know the first law of thermodynamics, that first law of thermodynamics clearly states that if we give heat to a system, del Q heat we give, okay, then it will be used in two ways: del U plus del W, to raise the temperature, to raise the internal energy, and to do some useful work. So, and we can write this change in work done. The work done is P delta V. For a constant volume, gas at constant volume, that this work done will be zero, because the volume is fixed. So all the energy will be used up in raising the internal energy, the raising the temperature. Okay, so clearly, because all the contribution in constant volume is going to the raising the temperature, so very less heat is required to raise the temperature at constant volume by 1 degree Celsius. But in case of a constant pressure, it will be used to do some work, because volume is not constant there. So clearly we can see that CP is much greater than CV, and we can also derive this. We have derived this, that this is CV is equal to CP is equal to CV plus R, where R is the universal gas constant. So let's begin this derivation again. For monoatomic gas, the molecule of a monoatomic gas has only 3 translational degree of freedom. Okay, thus the average energy of molecule at temperature, we have seen that in the previous chapter, previous video, that monoatomic gas has 3 degrees of freedom. That is, it can have 3 coordinate to define it, or it can do 3 translational motion, and each degree of freedom contribute to half kT. We have seen in the law of equipartition of energy. So the energy, the average kinetic energy of the molecule at T will be 3 by 2 kT. The total internal energy of a moles of such gas is, okay, so for 1 mole what we'll do, we'll just multiply this for one molecule. Remember, whenever we'll talk about one molecule, we'll say this Boltzmann constant, and if we multiply with this with Avogadro number to obtain the for 1 mole, and kn into n, this is R, universal gas constant. So just the thumb rule is, if there is R, we're talking about mole, 1 mole, and if there is K, we are talking about one molecule. Okay, so this is 3 by 2 kRT. This is the total energy of 1 mole of a gas. Now for the molar specific heat capacity constant volume, CV, as I told you, what is CV? This is the heat given to, you can it did, they have did it straightforward. I'll just explain it in detail. So suppose heat given this du, it will be used as I told dq, sorry, it will be used on du plus dw. For constant volume, the work done is 0, so dq is equal to du. Okay, and to raise the temperature by 1 degree dt, we have divided by dt. Okay, so this is dq by dt is du by dt for constant volume. Cv is what? This is Cv. Okay, so this Cv is du by dt. Okay, internal energy do not depends in volume, it only depend on temperature. Okay, so this is du by dt, and u was what? 3 by 2 rt, 3 by 2 rt. Okay, so cv will be how much? Cv will be 3 by 2, it should be r when we differentiate with respect to temperature, 3 by 2 r. This is cv for monoatomic gas. For an ideal gas, as I told you, cp is greater than cv, cp minus cv is r. So cp will be how much? It will be, just add r, and it will be 3 by 2 plus 1 is 5 by 2 r. So for a monoatomic gas, this Cp is 5 by 2r, and we take this ratio of specific heat, this will be Cp upon Cv 5 by 3. So for a monoatomic gas, this is the ratio. It is comes out to 1.66 approx, 1.67 approximately. I hope this was clear to you. We can do diatomic in the separate videos. Okay, thanks for watching.